Okay, so in the last class we have started with the waveguides, right? So in the waveguides we have seen the theory part first, and we have started with the parallel plate waveguide, and then we tried to solve the wave equations, and we have been obtained an equation for the electric field, and thereby we have defined the propagation constant and the phase velocity, and even then the different what you can say it is a modes of operation, and then we have discussed about the wave angle. And we have seen the different type of transverse electric, transverse magnetic, and transverse electromagnetic waves. So if you recollect once again what we have discussed in parallel plate waveguide, we are having that whatever the wave, it is trying to expand out in all the directions. So in the discussion of parallel plate waveguide, we try to restrict the expansion in the x direction, and thereby I said in rectangular waveguides you are going to keep another set of plates in y direction also. So the wave is going to expand in, you are going to restrict the wave in 2 dimensions, and rest of the things, everything is simple. And especially there is a change in the propagation constant and equation in the cutoff frequency. And other than that, everything is same. Okay. And what we have discussed in transverse electric, did you remember? So what I said when I was discussing about transverse electric wave, you can reply. So in case of a transverse electric wave, I said that if the wave is propagating in the z direction, the transverse electric represents there is no electric field in the z direction. So for transverse electric wave, you should not have any Ez component. Similarly, if it is a transverse magnetic wave, your Hz value will be equal to 0. And similarly, when it is transverse electromagnetic wave, I said that there is no electric field along propagation, and even the magnetic field also you don't have. And one more important point you have concluded that time, that the transverse electromagnetic wave cannot propagate in parallel plate and rectangular waveguide, because when it is trying to enter inside the waveguide, it is trying to enter at an angle of 0 degrees. Since your wave angle is basically said to be 0, using the definition of wave angle, your cutoff frequency is going to be 0 Hertz, which requires the dimension to be approaching to infinity. Okay, so that is the reason why if the transverse electromagnetic wave has to be propagated, you require a waveguide with a maximum dimension of infinity. So that is possible for free space. Okay, and even the same case, even that TEM wave cannot propagate in rectangular waveguide because the dimensions are said to be bounded. Okay, so now we will start with the rectangular waveguides. Okay, what is the difference in rectangular waveguides? So in parallel plate waveguide, you already seen there are 2 conducting plates located at x equal to 0. You can see the bottom plate, and x is equal to a, that is the top plate. So the modification in rectangular waveguide was I was introducing another set of plates at y is equal to 0 and y is equal to b, and assume that the wave is propagating along the axis of the rectangular waveguide. So there is no change in the direction of propagation. It is happily propagating along the z direction. So if you remember in the last class, I have told you when the wave is propagating in x direction. So when you see the classical mathematics, we have arrived at one of the equations says gamma x square is equal to gamma bar square plus omega square mu naught epsilon naught. Okay. So now the only change here is in rectangular there is another dimension y. So the equation is going to be modified as something like this. I don't know how many of you remembered. I said this point that I will repeat this thing in rectangular waveguide. So till this particular thing you have seen in the parallel plate waveguide. Okay, that time only I told you when I go to the rectangular waveguide, this equation I was going to slightly modify. Okay. So what is the value of propagation constant along x direction? Can you reply? What is the equation we got for the propagation along x direction? Can reply anybody? What is the propagation along x direction? What we got? I think nobody is replying, which means you would have been not gone through the theory part, right? Have we gone through the theory part? Yes or no? I request everybody to reply here. Have we gone through the theory or the recorded lecture at least? Because due to some urgency, I haven't been uploaded the PDF. Okay. And I hope you would have been gone through the theory part. Okay, that is very important. Now, first of all, you can answer my question. Have we gone through the theory, last class theory part? So tell me, whoever has done, so what is the propagation along x direction we got? What is the propagation constant, gamma x value? You can turn on microphone if you know anything. Try to waste the time.
So that is equal to root of gamma bar square plus omega square mu naught epsilon.
No. What I was asking here was when you are talking about gamma x, you remembered I have applied the boundary conditions at x is equal to 0 and x is equal to a. Okay. After doing that, we have got one equation for propagation along x axis. It is good. It is an integral multiples of pi by a. Isn't
Yes,
it?
sir.
Yeah. That's what I was asking. Okay, fine. In the same way, what is the value of gamma y? You can reply.
M pi by b, sir.
Yeah, correct. You can say some integral multiples of pi by b. Okay, thank you. Now, so you know the value of gamma x and you know the value of gamma y, right? So ultimately, since the wave is propagating along the z-axis, you can see here, the wave is propagating along the z-axis. So when I say the resultant propagation, that I have defined it as gamma bar, right? So when I say the propagation constant, even though the wave is passing through several reflections, if you see here like in parallel plate waveguide, though the wave is traveling in multiple directions, you can see here the wave is advancing in the z direction itself. Of course, it is not passing along the z axis, but it is taken a multiple path and ultimately it is advancing in the z direction. So when you see the propagation constant along z direction, okay, what you are going to get is in the equation gamma bar is equal to root over m pi by a whole square plus pi by b whole square minus omega square mu naught epsilon naught. So this is a propagation constant. The only change in parallel plate waveguide was since you are in the y direction, your n value is going to be equal to 0. Whereas in rectangular waveguide, you are keeping the set of plates in y direction. So that is the reason why there is an addition of n pi by b. Now again the same thing, right? So what will happen when the first term is higher than the second term? So suppose if this term is higher than this term, can you expect propagation? quickly. If suppose this is going to be higher value compared to this, in that case, you are going to get gamma bar is purely real, which means you are going to get attenuation. So in order for the wave propagated in a waveguide, you don't want that case to be happen. So you can say that in order not to have any attenuation, your gamma bar has to be purely imaginary. Okay? That can happen if omega square mu naught epsilon naught should be greater than or equal to m pi by a whole square plus n pi by b square. Okay, if this frequency is satisfying this condition, then you can expect that your gamma bar is purely imaginary, and in that case there is no attenuation. So what is this condition says? All the frequencies cannot be passed in the rectangular waveguide also. Only the set of frequencies which satisfy this condition can have an attenuation of 0. So in the same way, you can define the cutoff frequency. Sorry, this is not propagation constant. Okay, you can strike out that. This we are going to define it as a cutoff frequency. So how to define cutoff frequency? Just you can see this equation. When you are equating these two terms, you are going to get the minimum frequency. Okay. Now, so when I equate those two and arrive at the equation, so omega square mu naught epsilon naught is equal to m pi by a whole square plus n pi by b whole square. So which means you can say omega c square is equal to 1 over mu naught epsilon naught m pi by a whole square plus n pi by b whole square. So can you reply what is this term called? 1 over mu naught epsilon naught? Is it c or c square? Good. It is c square. Okay. That is equal to c square into the same thing. From this, can you do the calculation and tell me the final value? You can go ahead and tell me what is the cutoff frequency you are going to get. Okay. So when I say omega c is equal to c into root over m pi by a whole square plus n pi by b whole square, and omega c is written as 2 pi fc is equal to the same thing. So I can take pi square common from the square root, so it is going to become pi itself. Pi gets cancelled. So the equation for cutoff frequency, you are going to get it as c by 2 root over m by a whole square plus n by b whole square. Okay. But as I said earlier, one time you go through the derivation part in EMT. Okay. And the next thing is, once you are comfortable with the approach, so when I say it is a important equation, you have to memorize it. Okay. So now what is the significance of this cutoff frequency represents? That is what main important here. When you want to assume the propagation to be happen, if the frequency is below the cutoff frequency, you don't have any propagation. And if your f is greater than fc, you can expect the propagation to be happen without any attenuation. So the same characteristics what we have seen in parallel plate waveguide. So even in rectangular also, the characteristics will be high pass filter. Now you can cross check whether the same thing we done in parallel or not, just by substituting n is equal to 0. So when you substitute n is equal to 0, you are going to get an equation of mc by 2a. So you can see here, you are going to get mc by 2a. So that is the only change. Okay. So this is very important equation. You can see here in waveguide, if you are solving the problems, you can find out there are only 4 to 5 formulas will be there. But you require the basic fundamental understanding is required. Though I have said in parallel plate waveguide like TE, TM and TEM, you need not remember those equations. But what you should know in that case was you should be able to understand what is transverse electric, transverse magnetic and electromagnetic. The memorizing equation is not so important and you can find it out anyhow while solving the problems. Okay. So the next case, in the same way, I don't want to elaborate the complete things and all. So apart from cutoff frequency, your phase velocity and the wave angle definition, everything is same. But if you remember the approach what I have given to find out the equation for transverse electric, you have taken the Maxwell's equations, that is curl of A and curl of H. Okay. And then you are going to get some 6 set of equations there. After equating AX coefficient, AY coefficient and AZ coefficient. So since you are having 2 Maxwell's equations there, total 6 equations are there. And after solving that, you are going to get these kind of equations in rectangular waveguides. But what I'm telling you here was, you need not to memorize this. Okay, I will give a simple shortcut. Suppose by mistake, if you are unlucky people, and if they say that some questions like this, they will give an equation for electric field, and they may ask you to find out in which mode it belongs to. So that time it is going to be tougher. Okay, so I will give a simple approach, and it's a shortcut I can give you. So without deriving these equations, you will be able to write the equations. There is no derivation required, and just with the help of shortcut, you will be able to define what all these parameters and all. Okay, first I will tell the shortcut and I will come back to these equations. Okay, and I need your complete focus here to understand this shortcut. Okay, and this same shortcut is valid even if you go for the parallel plate waveguide also. Okay, actually what happens in rectangular waveguide, talking about a transverse electric wave, what it means, if the wave is advancing in the z direction, your Ez is going to be 0. That condition is there. So apart from Ez, everything will exist. Ex, Ey, Hx, Hy, Hz. But that's quite different when you see in the parallel plate waveguide. So there are only 3 components exist there, whereas in rectangular 5 components exist. That is because you can understand if you solve the real Maxwell's equation. Okay. But forget about that. Now I want to write a particular component. So let me write, I have to define the electric field in x direction. Okay. So what is the shortcut says? You can see clearly, you are writing the electric field intensity equation, right? So you should write the variation in 3 dimensions, along x variation, y variation and z variation. So first thing, when you are talking about z variation, we already know the electric field is trying to exponentially decrease with increase in z. Is a tendency of any electromagnetic wave. As the distance progresses, it has to exponentially decrease. So you have written already what is the variation of z. Is that part clear for everybody? I was telling a shortcut by taking one example. So in that case, if I want to write the electric field intensity in x direction, this equation should consist of all 3 variations. Okay. So first, when I was writing the z variation, you know that it has to exponentially decay with respect to z. Is it clear for everyone? So next thing you focus here. Suppose when you want to write the variation in the x direction. So suppose if you want to write the variation in x direction, you see the shortcut. First thing what you have to do was, since this is an electric field component, Okay, since this is an electric field component, this first shortcut is going to be valid. Okay, suppose if you are writing the magnetic field intensity equation, then you have to go for the second one. This second one is valid. So in this case, you are writing electric field in x direction. Okay, so your first shortcut is valid. And when you are writing the x variation, you should consider this plate only. So what is that? You had two set of plates at x is equal to 0 and x is equal to b, right?
Sir,
So with respect, yeah,
wave is propagating in which direction?
wave is propagating in z direction, right? There is no change in the wave propagation.
Okay.
Yeah. See here, I have told you. Let me go back to the slide. You can understand better. Yeah, you can see in this case, whatever you are seeing in the top and bottom is x is equal to 0 and x is equal to a. And y is equal to 0 and y is equal to b will be the side plates. Okay.
Okay.
Now, if the wave is moving like this, what axis you are moving? X equal to 0 is the top plate and y is equal to b is the side plates. So when you are going in this particular case, let us assume that there will be a variation is happening. Okay. This is the variation you can see here. This is your xy plane. Whatever the front face you are seeing is the xy plane.
Okay.
Now you got it right? Yeah. Now when the wave is propagating along z direction, okay. So to write that variation, I has come back to this shortcut. So when you are writing what variation is going to happen in x direction, you should consider the plate in x direction. Okay. So first of all, what you are going to write? You are going to write the electric field in x direction. So when you say your x is equal to 0 plane, what is the tangential component?
Z and Y, sir.
Yeah. So I have represented with a black color here. So both represents a tangential component. And which is going to be perpendicular?
X, sir.
Yeah. So that will be your normal component, right? Similarly, when I say y is equal to 0, if you write the y variation, you should consider this plate. So with respect to y is equal to 0 plate, your x and z will be tangential and y will be normal. So now let me first write the variation of electric field in x direction. So first of all, there is one thing here, which is your intended direction.
Yes.
Intended direction means which component you are writing. That means you are writing the electric field in x direction.
Okay.
In that case, x is going to set to be intended direction. Okay.
Okay. So for this case, it will be like
See, when you consider the x is equal to 0 plate, it is normal. Correct?
Yes.
So when it is electric field and it is a normal component, you are going to get cos.
Oh.
Okay. So first variation will be cos of, you know that the variation will be gamma x into x or gamma y into y. Okay. In the first class, if you remember, I have given an equation there. If you see that, you are going to get the variation like this: C1 sin gamma x into x plus C2 cos gamma x into x. Okay. Inside the bracket, what you are going to have is either gamma x into x if you are writing variation, and if you are writing y variation, you are going to get gamma y into y. Okay. Now let me write the y variation. It will be clear for you. Your intended direction is x. But when you are writing the y variation, you should consider this plate. So with respect to this particular plate, your x direction is said to be tangential or normal? Can you reply?
Tangential, sir.
Yeah. So if it is tangential, what component you are going to get? Anyhow, this is electric field, tangential, then you are going to get sign variation. So which means, say the value will be sine of gamma y into y. Okay. And then there is only, if you see the multiplier, if you see here, there will be some multiplier will be there for this. That multiplier will be depends on either TE or TM. So suppose when you are writing the equation for EX in TE mode, The multiplier will be whatever the coefficient inside the sine component. Right now, inside sine component, you will have a coefficient of gamma y. Right? That gamma y is going to be appear as a multiplier. Okay. Is it clear? Or otherwise, I will write one more equation. You can understand it better. Okay. Shall I do that? Yeah. So you randomly tell me which component you want. I will tell you the shortcut. You will go back and verify whether it is correct or not. You tell me component I have to write. Hx. So let me write the Hx component in Tm mode. Okay. Let me go back to Tm only. You can understand. So when you are writing the equation in Tm, first thing you are asking me to write Hx component. So first of all, I need to write X variation, Y variation, Z variation. So in Z variation, I can clearly say Hx naught into e power minus gamma Z. Okay. And if I want to write the variation in X, let me focus this particular plate. According to this particular plate, your intended direction is X. So when you consider this particular plate, that X component is tangential or normal?
Normal.
Quickly. Yeah, normal. But in this case, which case you have to take? First case or second case?
Second case.
Yeah, because it is magnetic field, you have to take this case. So in magnetic field, and since X is normal here, if it is magnetic field and it is normal, you are going to get sine coefficient. So the first variation you are going to get it is sine gamma x into x. Okay, what about y variation right now? So x variation over, z variation over. Now, when you are writing the y variation, look on this particular plate. So when you look on this particular direction, since again your intended direction is x. So with respect to this plate, x will be your tangential. So when you go back to the magnetic field and tangential component, you are going to get cos gamma y into, and there will be a multiplier. So what is that multiplier here? So since it is a transverse magnetic wave, what is there? Gamma y is there. So the multiplier will. Okay. Is it clear? Yeah. That's how you have to write. Okay. Now what you do, I will give a sufficient time to write down. Okay. I will clear it. And this slide will be open for all of you. So first, let us take one by one. So if you are writing TE, transverse electric equations, your EZ will be 0. Okay. And I want to get EX, EY, HX, HY and HZ. Okay. First you write down all the equations for TE using the same shortcut, whatever I told. After that, one by one, you can switch on your microphone and tell me what all the answers you are getting. Once anybody done with that, you can reply. Okay, you take time and do it. You need to do.
So H.
Sir, if transverse electric, then what will be magnetic? It will be what we will be transverse
No,
or
back. Only
Hello.
multiplier.
Hello, sir. Your voice is breaking. Hello.
Yes, sir.
Audible?
No, sir.
No. Are you able to hear me now?
Yes, sir.
So magnetic, you know. So when you try magnetic, this is shortcut. But only the change is what? Multiplier.
Okay.
Yeah.
Okay.
So everything, all these equations remain same except
Okay.
for the
Okay. Got
multiplier.
it. Okay. So if
Yeah.
it is transverse electric means always the multiplier will be inside the sign
Is
term.
sign coefficient. Yes, yes, yes. Correct. That is the only change. There is no change for TM.
Okay.
Yeah. So now you can reply HX. Anybody?
So
Yeah. First
H
variation.
X naught sin gamma x into x,
Yeah. Correct.
cos gamma y into y.
Good. Multiplier.
So multiply, I am not very clear with.
So multiplier, you can see you are writing the equation for TE, right? You
Yes,
are
sir.
writing the equation for transverse electric. When you are writing the equation for transverse electric, you should consider the coefficient which is inside the sign term. In this case, inside the sign term which is there.
Gamma x.
Yeah, that will be your multiplier. That's it. Yeah, good. So others, HY and HZ lost. Others also can reply. Yeah,
Sir,
yeah.
for HY,
First component,
it's cos,
good.
and the second component is sine,
Yeah,
and the multiplier,
multiply.
the one inside sine, so that is gamma y.
Correct. Okay, thank you. Thank you. So all of you please cross check. Okay, and the last one, HZ. Yeah, tell me. Tell me, Amrish.
Yes, sir.
Yeah, tell
Sir,
me.
we'll have HZ.
Yeah,
Okay, only EZ will be 0. So no,
hmm.
HZ 0, then it is tangential. That is
Try.
tangential in case of that is cos gamma x x,
Hmm. Okay,
and there also it is tangential. Then again it will be cos gamma y into y.
correct. So since there is no sign term, no, you can assume the multiplier is 1. So there will not be any multiplier. That's it. Okay. Yeah. Now these are the same equations what I have done in the previous case. Okay. So when you see this equation, this is what I have given. The only change what I have done was, you know that gamma x is equal to m pi by a and gamma y is equal to n pi by b. So I have replaced that values and as everything remains the same. You can see here, same thing. HZ you are going to get both are cos. Okay. So have you understood the concepts?
Yes, sir.
Yeah. And the next thing is the dominant mode. Okay. So when you go to the dominant mode, what is the definition I have defined in the last class? The dominant mode, first of all, when you see the mode is represented with a 2 subscripts. So when I was talking about a dominant mode, 2 conditions I have given there. The first condition was the dominant mode is the one which should represent the minimum value of M and N for which at least one electric field component and one magnetic field component should exist together. First case, suppose if I take m is equal to 0 and n is equal to 0, does it have any meaning? You can reply. Yeah, you can tell me. Does it have any meaning when I take m is equal to 0 and n is equal to 0? Yeah. I told you in the last class only. Both cannot be 0 at the same time. Because which means that there is no electric field in x direction and no electric field in y direction. And of course, since the wave is propagating in z direction, you should never have electric field in z direction. Okay, which means that the wave is not existing at all. Okay, so this case is ruled out. Now what you do, you take m is equal to 1 and n is equal to 0. So in that case, which component are existing, you can tell me quickly. When you put m is equal to 1 and n equal to 0, your gamma x m pi by a is non-zero. Okay? And your gamma y is equal to n pi by b, which is equal to 0. Okay? So first, when you put m is equal to 1 and n is equal to 0, I will quickly go through that. So what happens to the first term? Consider this case. First term is going to be 0 because your n is 0. And what about second component? It is going to exist. Third component is also going to exist. And fourth one is 0 because your n is equal to 0. And fifth one is equal to 0. So you can say that you can see one electric field is existing at least, and of course magnetic field also more than one is existing. So I can call that as a dominant mode, technically speaking. Am I right?
Sorry, if you will have 0, 0, then h of z will exist. So it will not be a dominant mode.
No. You should have two components, right? One electric field and one magnetic field, both should exist.
Oh, okay. Yes, sir. Yes,
Yeah.
sir.
If there is only one magnetic field, there is no meaning. Wave cannot propagate, right?
Oh, yes, sir. Yes.
Yeah. So now, as per the condition is concerned, I can say that m is equal to 1 and n is equal to 0 can be considered as a dominant mode. Okay. In the same way, even if you do m is equal to 0 and n is equal to 1, then what will happen? Then the first component you are going to get existing because m is equal to 0. Second component not existing. Third component vanishes. And fourth component will exist. And fifth component is going to become exist. Okay. This is also satisfying. Okay. Now, as per the technically speaking, you cannot say when out of 1 0 or 0 1 which is lower or higher. So I can say TE10 and TE01 both are dominant modes because it results in one electric field component and at least one magnetic field component. Okay. So in that case, which you should consider it as a dominant mode is basically depends upon the dimensions. Why? Because I said that when the first condition has not giving you the correct picture, the second condition you have to see. The dominant mode should have a least cutoff frequency. Correct? If you remember there, I have given the second condition as whenever you say something as a dominant mode, the cutoff frequency should be very minimum. Okay. Now, if you take a rectangular waveguide of dimensions A, which means A is the distance in x direction and B is the distance in y direction. What is the cutoff frequency equation I given? C by 2 root over m by a whole square plus n by b whole square. So subjected to that, for a TE10 mode, what is the cutoff frequency you are going to get? So in this case, substitute m is equal to 1 and n is equal to 0. You are going to get the cutoff frequency as C by 2a. Now, What is the condition I said now? If I say that TE10 mode is the dominant mode, my cutoff frequency has to be minimum. This is possible provided your A will be higher. So what is the condition? Your A should be higher than the other dimension. Similarly, when I say TE01 is the dominant mode, what should be the cutoff frequency right now? You are going to get C by 2B. Okay. Now, in order to have lowest cutoff frequency, my B dimension should be higher. Okay. That should be A less than B. Okay. The conclusion here is, when any problem is given in rectangular waveguide, and if they say a dominant mode, based upon the dimensions, you should choose whether it is TE10 or TE01. If A is greater than B, then you should consider TE10 as the dominant mode. And if your A is lesser than B, your TE01 is said to be the dominant mode. Is it clear? Because why I have tell this condition was, when you say TE10 mode is the dominant mode, your cutoff frequency is minimum if your A is higher. Because for dominant mode, the cutoff frequency has to be lesser. So that is possible provided if you take TE10 dominant mode, your A should be greater than B, and TE01 when A should be lesser than B. Is the concept clear? Yeah. Similarly, when you go to the transverse magnetic waves, you follow the same shortcut and please verify all these things. So when you go for the transverse magnetic waves, your Hz is going to be equal to 0. So which means there is no magnetic field along the propagation. So other than Hz, all the components you are going to have. Okay. But what is not there in TE and which is there in TM? Can you tell me? Out of TE and TM, I have given 5 equations. There is only one equation which is exactly different. What is that? There is only one change between transverse electric and transverse magnetic. What is that?
It can be 0, 0, sir.
Which one?
We can have 0, 0, sir.
No, I'm not talking about that. Out of all these components, I was telling you, right? 5 equations you have written, 5 components, right?
Yes,
So out of these, 4 components are common when you see in TE. Which is not there in TE, you tell me. In TE, do you have EZ in TE?
no, sir. No, sir.
Yeah. So in TM, instead of HZ, there you have discussed in TE, you will have EZ here. Okay. If you want to write EZ here, of course, if you see the transverse magnetic, there is no EZ here. Okay. What to do now in that case? We go back to the same shortcut. So first let me write EZ. How to write? EZ naught. Variation will be e power minus gamma z into AZ cap. So what is the first variation? When you see with respect to this plate, your z direction is a tangential. So in case of electric field, if it is a tangential, you are going to get sine. So the first variation will be sine gamma x into x. What is the second variation? So with respect to this plate, your z direction will be again tangential. Again, it is electric field and it is a tangential. You are going to get sine component. So that will be sine gamma y into y. And since it is for the transverse magnetic wave, the coefficient you should take whichever is there inside cosine. So since there is no cos term here, you can take multiplier as 1. Okay. So you are going to get both sine. So you can remember now, it will be helpful while solving the problem. When you have both sine, it is transverse magnetic wave. When you have both cos, it is TE, transverse electric. Okay. And remaining things and all everything already you have written in transverse electric, but when you are writing the same equation for Tm, just change the multipliers. All these component exactly will repeat except for the multiplier. Am I right? So you can verify the same thing after the class. Just I have written the same, copied the same equation just by changing the multiplier. What you have to do, first tell me when you take m is equal to 0 and n equal to 0, it doesn't exist. So verify whether m is equal to 1 and n equal to 0 is dominant mode or not. Okay, let me verify. M is equal to 1 and n equal to 0. So when you put n equal to 0, what happened dx? So since sine of n pi by b is there, if n is equal to 0, your sine term is going to become 0. So the first component vanishes. So what about second one? Multiplier n is there, vanishes. Third component, again sine of n is there, vanishes. Fourth component, multiplier n is there, not exists. And again the fifth component, of course there is again term will be there, so which is vanishes. Okay, similarly even you can check m is equal to 0 and n equal to 1. Okay, when you put m equal to 0, first term will be anyhow straight away 0. Second term also sine of m will be there, so that is 0. Third one again sine m term will be there, 0. Fourth one sine of m, 0. Fifth one is also 0. So when you put m is equal to 1, n equal to 0, m equal to 0, n equal to 1, none of the component are existing. So what should be the minimum value of m and n right now? When you put m is equal to 1 and n equal to 1, all the components are going to exist. So it is satisfying the definition of dominant mode. So in case of a rectangular waveguide, if it is a Tm, dominant mode is Tm11. Is it clear? So when I summarize this and all, so for TE, the dominant mode is both TE10 or TE01 based on the condition. And for Tm, the dominant mode is 11. Is it clear? Okay. So that is the only change. Other than that, everything is same. You won't get anything difficulty. Okay. Now we'll try to solve some simple problems. Then you can really understand. Okay. There are so many derivations are there in the waveguides, but it is not required while solving the problems. As I said in the first class only, before starting waveguides, okay, here you have to understand the concept, but when you go to the problems, it is straight away, it's a formula based or some little bit understanding is required. So you won't find anything difficulty. Okay, read the first question and you try to solve. So there is a 10 gigahertz signal propagates in a waveguide with a phase velocity of 4 into 10 power 8 meter per second. If the signal produces a standing wave inside the waveguide, then find the distance between two successive minima. So if assume that this is a waveguide, and if the wave propagates inside this, you can see that there is a standing wave. So first of all, the standing wave is existing because the waveguide, whatever the wave it is traveling, it is possessing some impedance. I will tell you how to find out that impedance later. So whenever the wave impedance is not matched to whatever the load you will connect, there will be a standing wave. I hope you would have been understand what is standing wave and what is the reason. we have in transmission line, we have done an extensive discussion on what is standing wave and all. So whenever an impedance mismatch happens, there is a standing wave produced. So what is this question? It says, in that standing wave, so the distance between two successive minima, you can see here, this is your standing wave. The distance between two successive minima is equal to, you have to find out the distance between successive minima. So tell me, what is the distance between two successive minima we got in transmission lines? What do you remember? What is the distance between two successive minima or two successive maxima in a transmission line? Good. It is lambda by 2. So the same thing here also lambda by 2. But since the wave is propagating inside the waveguide, it should take the wavelength as a guided wavelength. Okay, that should be lambda g by 2. That is the only change, because everybody will be getting confused because the standing wave has been produced inside the waveguide. So once the wave is entered inside the waveguide, you should take the guide wavelength into picture. Okay, not the free space wavelength. So how to find the guide wavelength? Using the phase velocity. Because in the phase velocity you have defined, it is nothing but the guided wavelength times frequency is equal to 4 into 10 power 8 meter per second. Okay. So what is the guided wavelength you are getting right now? That is equal to 4 into 10 power 8 divided by frequency is 10 gigahertz. So which means that 10 power 10. So you are going to get lambda g is equals to 4 into 10 power minus 2 meter. Okay, you can say 4 centimeter or 40 mm. The answer is exactly, the answer is not 40 mm. So this is the guided wavelength and the distance will be lambda g by 2. Okay, you are going to get the answer as 20 mm. Is it clear? Any doubts here?
No, sir, clear.
Yeah. So next, go to the next one. So there is a rectangular waveguide having a dimensions of 3 centimeter by 4.5 centimeter. Okay. And a 9 gigahertz signal is propagating in it. Then find what is the cutoff wavelength for the TE10 mode. So if you can do that and you can tell me. So there are two approach method. One is your concept and the second one is the mathematics. Can you tell me what is the answer? Quickly do it, no problem. And tell me once you are done with that. Or somebody at least tell me what is an approach to follow. If you're not able to do, not a problem. Tell me the approach, what you have to do. How to find the cutoff wavelength. Can you tell me the approach, anyone?
So what will take VP here?
Which one?
Cutoff.
What is the
You can
cutoff
give-
wavelength first of all?
Sir,
Once
it
you know
is
the
a
cut, once you
frequency
know
we
the
need to find.
cutoff frequency, you need to find out. Correct?
Yes, sir.
Yeah. After finding the cutoff frequency, how to find the wavelength? If
So we do
nothing
not
is
have.
given, you can assume it as a free space. Okay.
Okay, okay. Then we can find that is
C divided by FC, right?
yes, sir. Yes, sir.
Okay. Yeah. So what is the answer you got doing that? 6 centimeter. Yeah. Okay, but that is an approach if we go in a classical method. Okay, but you have to understand the theory, what I say. First of all, what do you mean by TE10 mode represents? In the x direction, there is one half cycle of electric field is present. And in the y direction, there is no variation. So since there is one half cycle in the x direction, okay, and in x direction, what is the distance here? This will be 3 centimeter. And since it belongs to first mode, there is only one half cycle is present. So when one half cycle is present, you know that the distance between these two is exactly equal to lambda by 2, because only one half cycle. That is equal to 3 centimeter right now. So what is the wavelength you are going to get? 6 centimeter. So that is what the different. Actually, if we go in a conventional mathematic way, and if you really understand the concept, you can find out this approach is the easiest method. Is it clear?
Yes, sir.
So my suggestion was, first of all, when you read any statement, try to think it in a different way rather than following the conventional mathematics. Is there anything possibility that based on understanding you will be able to do it or not? Okay. So in the same thing, suppose if I say the mode is TE01 mode, what is the cutoff wavelength?
9, sir.
Correct. Good. So in that case, you should consider the y dimension. Because in x direction there is no variation. In y direction there is one half cycle. So in y direction the dimension is 4.5 centimeter. So your lambda by 2 is 4.5 and lambda is equal to 9 centimeter. So like that you have to do. Next problem. You can see here in an air-filled rectangular waveguide, the cutoff frequency for TE10 mode is given as 5 gigahertz, and whereas for TE01 mode is given as 12 gigahertz. Then what is the dimensions of the waveguide? Can you tell me quickly? You can do it and tell me what is the answer. Once you are done with that, you just share. Can it be done in a verification method? Is there anything possible?
Yes, sir.
Yeah. How to do?
So we'll use the same. That is lambda by 2 equals to that is x. Then again lambda by 2 equals to y. And lambda will do is distance by f, d by f. And d by f and c. The speed we have is 3 to 10
Velocity
to
of
power
light.
8. And for x we'll take the 5 gigahertz frequency, and for y we'll take the 12 gigahertz frequency.
Correct. So instead of that is not the actual shortcut. You are going in a classical method only. Okay. Anyhow, that is a good approach only. But actually, what I was saying, you know that what is the basic formula for cutoff frequency? In parallel plate waveguide only, I told you the cutoff frequency is equal to MC by 2A.
Yes.
Okay. Since it is 10, it is same as your parallel plate only, isn't it? Yes or no?
Yes.
Since you are setting the other dimension is 0, means it is a parallel plate waveguide only. Though it is mentioned rectangular waveguide, you can use the formula of parallel plate waveguide because the dimension is 0. So what is the cutoff frequency for 01? Straight away?
01 is 12. Sir.
Yeah? No. Cutoff frequency formula. The same thing. You compare with the parallel plate waveguide.
Okay,
In
yes,
parallel
sir.
plate waveguide,
2B.
good, correct. It should be C by 2B. So what you can do right now, basically what I am trying to say, if there is anything possible with the verification, you see first. Because in the first case I have given it as 5, in the second I was given it as 2. So if you take the ratio, you are going to get 5 by 12 is equal to B by A. Okay. Is it in that case your A by B is said to be 2.4. Is there anything matching or not? You can see. Based on that, you can find out. Okay. So which is satisfying? I think first option A and option B are satisfying. Okay. Again, it's a problem. If you do using options, option A and option B both are satisfying, at least you will be able to eliminate two options. See, because your A has to be higher. Okay. So forget about that. Now, let us do with a normal method only. Okay. So for TE10 mode, the cutoff frequency is equal to 5 into gigahertz is equal. And one more thing I will tell you here. So since all the rectangular waveguides are said to be in centimeter, dimensions are in centimeter, whenever you are substituting for velocity of light, you take it in centimeter per second. Okay. The cutoff frequency is equal to 5 into 10 power 9 is equal to, you take 3 into 10 power 10 divided by 2a. So where a is in straight away in centimeter. Again, you need not to take 10 power 8, convert meter to centimeter. All these things not required. So if you want to get the dimension in centimeter, take the numerator in 3 into 10 power 10. So now it will be simple. So what is the value you are going to get?
3.
3, yeah?
Yes.
Yeah, 3 centimeter. Good. So similarly, you can verify for 0, 1 also. Same thing. So 12 gigahertz is equal to 3 into 10 power 10 by 2b in centimeter. So what is the value you are getting? B. You can verify it is 1.25 centimeter. So you are going to get the answer as 3 centimeter by 1.25 centimeter. Okay. So I will go to the next problem then. So for the dominant mode in a rectangular waveguide with width 10 centimeter, then the guide wavelength for a signal of 2.5 gigahertz will be. So he has given the value is equal to 10 centimeter. Okay, but you don't know whether it is A or B. Okay, assume that it is nothing but A or B, something, whatever, it doesn't matter. But anyhow, if you see your rectangular waveguide, you will have A dimension and B dimension. So it doesn't have actually meant. Some people can say this as a width and some people can say this as a width. But forget about that. But when you are taking it in a dominant mode, so suppose if you take A is equal to 10 centimeter, you assume that the dominant mode is TE10. There are only two options, right? Either it should be TE10 or TE01. Okay. The other dimension has not given. So you assume that whatever the dimension given here is a maximum. So based upon that, I was assuming A is equal to 10 centimeter and I was assuming it is maximum. So when you are assuming A is maximum, your TE10 mode is said to be dominant mode. Am I right? Because see, suppose if you assume 10 centimeter as a minimum dimension, you cannot predict, you cannot find out. Dominant mode can be decided only when you know the maximum dimension. Okay, so that is the reason why I have assumed whatever given is my maximum dimension. According to that, TE10 mode is my dominant mode. Okay, then first of all, calculate the cutoff frequency. Everybody.
Here we cannot directly do the same way. That is, D is equal to lambda g by 2.
It's not lambda g, right? It is a cutoff wavelength. Guide wavelength is different,
okay,
right?
Okay.
Yeah. Here you cannot do. So first of all, tell me what is the cutoff frequency you got. So you know that the cutoff frequency is equal to C by 2A. And since A is in centimeter, you take 3 into 10 power 10. So, and A is in 10 centimeter. So what is the value you are getting? You can correct me if I am wrong. You are going to get 1.5 gigahertz. isn't it? Once you know the cutoff frequency, you know one of the equation I have given in phase velocity. So you can define the phase velocity in two methods. Either you can define it as a guided wavelength into frequency, or it is same as c divided by root over 1 minus fc by f whole square. So if you are not clear, you just go through the last class. I have given this equation. The phase velocity is wavelength times frequency, or you know it in terms of the cutoff frequency. Now everything values is known, right? Just compare these two equations. Now in order to get that, what I can do, the lambda g value can be written as c by f divided by root over 1 minus fc by f whole square. Now you know everything. So the frequency will be 2.5 gigahertz and your cutoff frequency is equal to 1.5 gigahertz. Okay, you substitute and tell me what is the value you are getting. First of all, is this signal will propagate inside or not? So you are getting f is equal to 2.5 giga and your fc you are getting it as 1.5 giga.
Yes, sir.
It will propagate, correct?
Yes,
Your
sir.
f is greater than fc. So first thing, whenever you are defining anything in waveguides, you know, this thing you have to verify. If f is greater than fc only, you will be able to analyze all the things. Okay. So then f is equal to greater than fc means you can go ahead. You directly substitute all these values. So if you want to get in centimeter means you should take velocity of light in centimeter. 3 into 10 power 10 divided by frequency is 2.5 gigahertz into root over 1 minus fc is 1.5 giga and f is equal to 2.5 giga. So do the calculation and tell me what is the answer you are getting. Do it quickly. What is the answer?
Sir, it will be sine.
Verify.
Sine 20 pi x
Ah,
and sine 50 pi y.
correct. Good. Yes. It is verified
But
because
the multiplier will not.
there is no multiplier, no? If both are same.
Oh, okay.
Both. So first thing you can see here, whatever there inside this one is gamma x, your propagation constant in x direction. This is the propagation constant in y direction. So when you see the equation, so what by comparing this one, what you can say, 3 pi by a into x is equal to 60 pi x. So similarly, n pi by b, which means 2 pi by b into y is equal to 100 pi y. So when you are writing the equation for 1, 1, what you are going to get? This first term is going to become 1 into pi by a into x, and second term is going to become 1 into pi by b into y. Okay, what you have to do right now? Just divide with 3, so you will get this one. Just divide with 2, you will get this one. So the first component, because this is 3 times of this is 60 pi, so 1 time of this one will be 20 pi. Similarly, 2 times of this value is equal to 100 pi, so 1 time will be 50 pi. Okay, you can get 20 pi x and 50 pi y. So with this way, you can verify the options. The simplest method was from 3 to 1 1. If you want to do means you just divide with 3 here and divide with 2 here over. Is it clear? Just from 3 to mode 2, you have to go back to 1 1 mode. So just divide first component by 3, second component by 2. Then it's corresponding to 1 1 mode. Any questions here? Shall I go ahead? is the next problem. So find the cutoff wavelength for TE20 mode for a standard rectangular waveguide of dimension A by B. Okay, these options are not given correct. Okay, you forget about this. What should be the cutoff wavelength for TE20 mode for a standard rectangular waveguide of dimensions A by B? So tell me quickly.
Lambda is equal to A, sir.
Yeah, good. Since it is TE20 mode, there are two half cycles of electric field in the x direction. So in the x direction, the spacing is A. You can see here the first dimension is A. And since you have two half cycles, the distance from here to here is equal to 2 times lambda by 2 is equal to A. So you are going to get cutoff wavelength is equal to A. The answer for this is cutoff wavelength is straight away A. Okay, same thing. Next problem. This is very important problem you can see here. An air-filled rectangular waveguide has the dimensions of 2 cm by 1 cm. Okay. Then find the wave angle for a frequency of 25 gigahertz. So first of all, when you want to define the wave angle, you should know the cutoff frequency. So first of all, since nothing is given, when you are finding out the cutoff frequency, in the question, it is not said whether it is a transverse electric or transverse magnetic. So if nothing is mentioned in the question, you have to assume it as a transverse electric. Okay. Not only here, there are so many times the question has been asked like this only. They will not say in order to find cutoff frequency, which one you have to choose it as a dominant. So if nothing is mentioned, so once again make a note, you should consider TE as a dominant mode. Now the question comes, is it TE10 or TE01? Can you tell me which one you should consider?
Sir, TE10 here because A is greater.
Correct. You should consider TE10 because your A is greater than B. So first what you need to do, you find the cutoff frequency and you know the wave angle equation. Sin theta is equal to Fc by F. So first find the cutoff frequency for TE10 mode and you know the operating frequency is 25 giga. So then wave angle can be defined. So please do that and tell me the answer. Okay, I will go to the next problem then. Please you see and tell me the answer. First read the question. Okay, anybody? First of all, if you see this equation, do you have what all the variations are there? If you see this equation, what all the variations are there? Here x variation only given, y variation he has not given. Straight away he has given z variation. Yeah. So first of all, what is the condition here? Since there is no variation in y direction, your second subscript will be 0. Agree?
Yes,
You don't know whether it is T or Tm, but it doesn't matter. The second subscript will be 0. Correct? And when you consider the first one, so inside sign what you are having? Generally, whatever the variation it is there, it is in the form of gamma x into x, which will be, you can say m pi by a into x here he has given the value is equal to 2 pi by a into x. So accordingly, you are getting m is equal to 2. So either it should be TE20 or TM20. But right now, how will you find out whether it is TE or TM? Can you tell me how to find out? Tell me quickly. Both sign component. No, it's not both sign component. This is a variation in z direction. So whatever I have given e power minus gamma z, right? So instead of e power minus gamma z, he was returning something like this. It's not both sign. This is the electric field in y direction. You can see this is the electric field in y direction. It's not both sign because y direction you don't have any component. You should see the difference. So there is a one simple trick. Whatever the coefficient you are getting here, it is nothing but your x component itself, right? Whatever there inside sign only you are getting as a multiplier. Agree or not? Whatever inside there in the sign, you are getting it as a multiplier. Agree with me? Yeah. Because of course 2 pi by a is there. I can multiply with 2 and divide with 2. This and all everything is a constant. If you are getting sign coefficient as a multiplier means is it TE or TM? Told you. Which case you will take the multiplier as the coefficient inside sign? Is it TE or TM? Good. It is TE. If you go back to the previous slide I given. So if you are getting the multiplier as whatever there in the sign coefficient, it is a TE. Suppose if you are getting the multiplier as whatever there in the cos, then it will be TM. So in this case, the answer is TE20. Okay, these are the cases where you have to memorize the equations. Okay, sometimes, but it depends on the luck again. So that is the reason why I thought I can give a shortcut for you. So which will be very helpful like solving in these kind of problems. Is it clear right now? So once again, I was repeating, if anybody not understood, just focus here. So here I have given the x variation, y variation is not given, and straight away z variation is given. But when you are writing any mode, you are writing x and y variation only. So since there is nothing given in y variation, you can consider it as a 0. And in x direction, you are getting the multiplier m is equal to 2. Straight away you can see. So it will be either TE20 or TM20. But what coefficient I have given here is whatever is there in the sign component. So if I are taking anything in the sign component as a multiplier, that will be of the type TE. If I are taking the multiplier as whatever is there in cosine component, the answer is going to be TM. Okay. So let's go to the next question then. So this also you just guess the option. Whether it is right or wrong, forget about it. Just guess what is option. So which one of the following does represent the electric field lines for TE02 mode? So just guess and reply here. Whether it is right or wrong doesn't matter. Just give me reply. What do you think? Is it option B? Okay. You see here how this kind of problems is solved, just see the variations. So this is your X variation and this is your Y variation. So again, same thing. What is the T02 represents? In X direction, you are having 0 variation, and Y direction, you will have 2 variations, right? Which is satisfying right now. So suppose when you are looking at option A, so all the flux lines are like this. So when you trace that, you can see here there is one variation here, which means that one maxima is there. So that maxima is observed when you are moving in this direction. Agree? So when you move along the X direction, you can see that all the flux lines are oriented towards you. That time, since all are oriented in only one direction, you can say one variation is there. So this is an example of TE10. Because when you are moving along Y, suppose if you are moving along this Y, are you able to see in which direction the arrows are oriented? So when you are moving parallel to the flux lines, you can remember there are no variations. So let me do it for B, then you can understand. So when you are moving in B, when you are moving along, yeah.
If you have two modes, mean two variation.
Yeah, I will tell you. Correct. Two variations. Or you
Why
can say
that?
two halves. That no. Generally, the meaning is like that. Whenever you are representing any pictorial representation, So
Okay.
when I was talking about T is 2-0 mode, what it actually says, between two plates, there are two half cycles are there.
Yeah. Oh, okay,
Correct?
sir. Okay.
So
One
which
positive,
means
one
that you can
negative.
say one positive, one negative. So which means the variation
Yes, sir.
like that. That's how it goes. So similarly, when you see the option B, when you move in X direction, will there be any variation?
No, sir.
Yeah, because when you are moving parallel, there is no variation at all. So what happened when you are in Y direction? All are oriented in Y direction only, isn't it? So in this case, what is an example you can say? X direction, there is no variation. Y direction, you can say one variation. Because all are oriented like this. So similarly, can you tell me for option C?
So we have variation only in X direction.
In?
X.
You don't have variation or you have variation?
We have variation in X.
No.
Yes, sir. We are going positive and negative. Both are there.
No. When you move in the X direction, do you have any variation?
Yes, first we are negative, then negative. So it will cancel
No.
each other, zero or what?
No. When you are moving in the X direction, you are moving parallel, right?
Okay.
When you move in the X direction, are you able to see where the arrows are oriented?
They are parallel to X axis. Okay.
Whenever it is parallel to the X axis, there is no variation. Okay.
Okay,
You
sir.
can observe the variation. Suppose if you are moving along Y, you can see that some will be located here and some will be located here.
Okay. Like
Yeah.
this.
You got my point now? See, you can see here some are oriented in this direction, some are oriented in this direction. So in this Y direction, you will have two variations. So this is an example of T02.
02.
Similarly, you see here the flux is oriented here. So here some variation and here some variation. So
Sir,
this
we
is an
have
example of,
given already X
yeah.
and Y. And again in
Huh.
that we need to draw the wave. Okay.
First you just see, based on the arrows, first you draw the wave. So the wave is observed when you are moving along the X direction here.
Yes, sir.
Yeah, in this case, it is an example of 2-0. Okay, because when you are moving along Y direction, you remember whenever you are moving parallel, there is no variation.
Okay.
Okay, I will give another example, then you can understand it better. Okay.
So for this one, the answer will be then T
C,
0
option
to
C.
C.
Yeah. In X direction, you don't have anything. Okay. So let me give this one, then you can tell me what is the value. Tell me this one.
Sir, this is T03.
Very good, very good. Correct. That's it. Because when you're moving along x direction, there is nothing. See here, some are oriented here, some are here, and again here. So which means that you can say 3 half cycles are present in y direction. In y direction, 3 half cycle means first one 0. So is it clear? The representation.
Yes, sir.
So see the next problem. So a air-filled rectangular waveguide has an inner dimensions of 3 centimeter divided by 2 centimeter. Then find the wave impedance for TE20 mode of propagation at a frequency of 30 gigahertz. First tell me, what is the wave impedance of a TEM wave, transverse electromagnetic wave? When you are talking about a transverse electromagnetic wave, I told you, when it is moving in free space, the impedance will be 120 pi. Isn't it? Now, what will happen when you want to define impedance for TE? Okay, I told you the transverse electric wave, recollect exactly, it is an example of the S polarized wave, or it is a perpendicular polarized wave where you will have the electric field in y direction and magnetic field on the XZ plane. So what is basically wave impedance is nothing but the ratio of transverse electric field and transverse magnetic field. So first when you see the waveguide like this, you see here, this is your parallel plate waveguide. And one is at x equal to 0 and x is equal to a. So the actual direction of propagation is like this. Okay. And this you are defining it as a wave angle. Right. Now what happens when it is a TE wave? How to represent your electric field in y direction here? You can see here the axis, when you are moving along the axis, this will be your z direction. And which one will be the perpendicular direction here? When you go in this particular direction, which one will be the perpendicular direction?
X, sir.
Correct. So when you consider this plate, you tell me what is this variation? So when you move from this to this, will you agree with me if I say it is Z?
Yes, sir. Parallel to Z.
Parallel to Z axis, correct? So this component should be Y in that case. Correct?
Yes, sir.
Correct or not? Now what you have to do, you can assume that your electric field lies in the y direction, but magnetic field should have in XZ plane. So if I want to represent my magnetic field, and if you want to suppose if you want to define the wave impedance, you should take the transverse component of electric field and transverse component of magnetic field. So that will be electric field in y direction divided by magnetic field in x direction. Agree with me? What do you mean by transverse? Whenever you are taking any wave impedance, it should be the ratio of transverse electric field by transverse magnetic field. Transverse means perpendicular component to the direction of propagation. So in this case, wave is propagating in the z direction. So when you take any component in z direction, that is called longitudinal component. And when you take any perpendicular component to z, that is called transverse component. So anyhow, in this case for transverse electric, your electric field in y direction is a transverse component. And since magnetic field consists of two components, what is that? One is your transverse component, other one is longitudinal component. But when you are defining the wave impedance, you should always consider both should be the transverse component. Is it clear? Is it clear or not? Anything needs to be explained. Yeah. Now the next thing, how to find out the value of Hx. So do you think that this is your direction of propagation, right? Actual direction of propagation is this. Do you think that the magnetic field also lies in the same direction?
Same direction means?
I mean, you're like this only, along the wave propagation.
Yes, sir.
No, your magnetic field also should have XZ components. Okay. But
Okay.
in that, having said that, do you think the magnetic field also propagates along the direction of propagation?
Yes, sir. So resultant
No.
will be a direction function.
Correct only. Your magnetic field definitely will have X and Z component. But I told you in the second chapter only, when the wave is propagating in a certain direction, your electric field and magnetic field should be perpendicular to the direction of propagation.
Okay. Yes, sir. Yes, sir.
Yeah. This is your direction of. So as per this, if you resolve, this is your Z component and one you are going to get X component for the direction of propagation. Suppose I will take the magnetic field like this. Does it have XZ component or not?
Yes, sir.
Now you can see here, this is my magnetic field and this is propagation. Perpendicular or not?
Yes, sir.
Yeah, that's how. So what is the confusion everybody is having here was, that's why I was clarifying it clearly. Even though your direction of propagation in XZ plane and your electric field in Y direction and magnetic field in XZ plane, what generally you used to think, since your direction of propagation also XZ plane and magnetic field also XZ plane, you may think that both will coincide.
Yes, sir.
But the actual fact is what? Your electric field should be perpendicular to direction of propagation. Magnetic field also should be perpendicular.
Okay.
Now, according to this one, is it correct or not? Whatever I have drawn, your magnetic field also lies in the XZ plane. Because you can see here, this is your Z axis and the perpendicular one is X axis.
Yeah, when we
So
take
when I
transverse means no component at all. Means like means it will be perpendicular, but will not have
no, perpendicular to the actual direction of propagation.
Okay.
I mean, even though the wave is propagating, ultimately it is moving, advancing in the Z direction only, right?
Yes, sir.
Of course, even though the wave is taking a longer path, ultimately it is advancing in the Z direction. Okay. Now, what I have done, when I take a magnetic field like this, if you resolve it, you will get Z component and you will get X component.
Yeah.
Similarly, if you resolve the direction of propagation also, you will get one Z component, one X component. Positive X or negative X, I am not bothering about it. Okay.
Yes.
Is it correct right now? In this case, now you know, this is very important. You concentrate here. This is your wave angle. This is your theta. Now, what is your Hx component? Whatever there here, this is the resultant magnetic field. You can see here, whatever I have drawn here is the resultant magnetic field. And when I say the magnetic field in X direction, because you are defined the wave impedance for TE as Ey divided by Hx. You should consider what is the magnetic field component in this direction. Okay. In order to do that, what you do, this is your Hx component and this is your resultant magnetic field, and then you can find out what is the value of Hx. So what I can do right now, whatever you are seeing in this triangle, okay, I will draw it vertically. So what I can do, I can draw it vertically. So this is my resultant component. And can you tell me what is this value? Are you able to see? So this is theta, right? What about this component? Are you there? -90 minus theta, correct. This is equal to 90 minus theta. Now, can you tell me what is the value of this Hx component? Use the trigonometry. You can draw it vertically and tell me quickly. So your magnetic field is perpendicular to the direction of propagation. That is the only condition here. No, can you cross? Is it H sin theta or H cos theta? Please cross check. See here, in this particular triangle, what you can see here, this is your Hx component and this is your Hz component. Okay, so let me draw it clearly, then you can understand better. So this is basically your wave angle, right? And your magnetic field is exactly propagating perpendicular to that. So this is your resultant propagation constant. Okay, and here there is a 90 degrees angle. So this particular component, you are going to get it. Okay, this is nothing but your Hx, and this is going to be your Hz. Okay. So anybody solved? You are getting cos theta or sin theta? Somewhere we are doing mistake. Actually, we should get cos theta. So can you cross verify where we have done mistake? So this is going to be your 90, correct? And this is going to be 90 minus theta I. This is going to be theta I. Okay, you are going to get cos theta I is equals to okay. What is the value you are getting? You tell me. E is equal to Ex by Hy. Just give me a moment. I will cross check whether any mistake you have done or not. So your electric field in y direction divided by magnetic field in x direction. So this is the magnetic field in x direction and this is your resultant value. Yeah, correct. So y divided by Hx can be written as, so when you are seeing here cos theta I, what is the value of cos theta I? You can get it as, yeah, cos theta I value can be get it as the resultant value. Let me say the resultant value divided by the hypotenuse. Correct. Yeah. So from this, the result Hx can be written as H resultant value divided by cos theta I. Correct. So the wave impedance for the TE equal to Ex divided by whatever the resultant value you are getting divided by cos theta I. Correct. Is it correct? So what is the Px divided by ht, correct. I have done confused here. So there is nothing wrong we have done. So let me explain it clear so that there will not be any doubt. So Ey component is clear. In order to get hx, see here, this is your hx component and this is your resultant magnetic field. So if I know the angle here, because this is already theta I, so this is 90 minus theta I. So this will be equal to 90. So this is going to be theta I. So when you are applying the value of cos theta I here, that will be equal to the resultant magnetic field divided by hx. So I can say hx component can be written as whatever the resultant component, that divided by cos theta I. Okay. In that case, your wave impedance can be defined as your wave impedance is equal to Ey by hx. Okay. Hx can be written as the resultant time divided by the cos theta I. So cos theta I can come in the numerator. So you know that Ey by ht is basically said to be the wave impedance in free space, because actually between the plates you will have the free space. So whatever the electric field in y direction and the magnetic field in the resultant direction, if you take, that will be equal to 120 pi. Okay, then you can substitute that value. So eta te, you are going to get it as 120 pi into cos theta. So first of all, how to find out this wave angle? Can you tell me how to find out the wave angle? The wave angle can be defined by the base of mode of operation. Okay, it falls in the second mode. So first calculate the wave angle. First of all, you know that sine theta is equal to fc divided by f. So calculate the cutoff frequency for the second mode. Do it quickly. So for the second mode, you are going to get it as 2c divided by 2a. mc divided by 2a, m is equal to 2. So what is the value? So substitute the values and tell me what cutoff frequency you got. So that is equal to 3 into 10 power 10 divided by 2 into a. So what is the value of a here? 3 centimeter. So you are going to get gigahertz. Okay. Once you know the cutoff frequency for this particular mode, okay, then calculate the wave angle. Yeah.
Sir, why we will take 2, sir? Why not 3 here divided by?
Which one?
Sir,
Here?
this 3 into 10
No,
to
no,
the
no.
10 by 2 into. Oh, yeah, got
Yeah,
it.
that's
Got it.
what I was.
Yeah, sorry, sir.
Yeah, m is equal to 2, right?
Yeah, yeah, yeah.
A, your m is equal to 2. Okay. Then here, see here, again, you should not apply the concept here. So, see, your wave is propagating in which frequency? 30 gigahertz.
Yes, sir.
Yeah. Now the question is here, you should not take something like this, 5 to 10 gigahertz in the first mode or 10 to 15 in the second mode and so on. Because he has specially asked for that. For T20 mode, explicitly you want to find the wave angle. Okay. This,
Yeah.
suppose if you are finding the
Yeah, yeah,
dominant
got
mode
it.
cutoff frequency, you should take the ranges. But if it is T20 mode, you should operate cutoff frequency. So what is the wave angle right now? So you can calculate sine theta is equal to fc by f. So that is equal to fc divided by f. That is equal to 1 by 6. Okay. Now from this you can get the value of theta I, right? So then you can apply in the formula. Whatever the eta te I have given, that is equal to 120 pi in free space into cos theta. Okay. So you can do that. You are going to get some value. Please cross check. Okay. I hope you can do it later. I was leaving it an assignment to you. So just verify after the class. So you came to know the what is the value of theta I, and you can substitute here in the formula. And there is one more small topic is there in the waveguides that we'll try to finish it. And in the next class, actually, the plan is we will dedicate it only for the antenna theory. Because antenna theory, it may going to take for 2 or 2.5 hours. So this part we'll try to complete today, optical fibers. And of course, it's a theoretical topic, nothing to discuss about that. Okay, so optical fiber is also a kind of waveguide, but are used in the frequency range of terahertz. No, when the frequency of operation is greater than 100 terahertz, you can see the optical fiber is the best preference. So suppose when you are talking about low frequency in the range of megahertz, your coaxial cables are preferred. So where all the information is in the form of voltage and current. And when you are talking about gigahertz, you are going for the waveguides. And when you are talking about terahertz, you can go for the optical fibers. And the main reason being why optical fibers are most preferred at very, very higher frequencies, nothing but because if you use a coaxial cable at very, very high frequency, what will happen? Can you tell me? What is the problem if you use the coaxial cable in the range of terahertz? Can I use the coaxial cable there? Yes or no? You can reply at least. Are you able to hear me? I'm not getting any feedback. So my question is, can you use the coaxial cable at terahertz frequency range? Terahertz means 10 power 15, more than that. Can you use that coaxial cable?
We can use.
Yeah. Generally speaking, when you are talking about very, very high frequency, if you take a coaxial cable, as the frequency is very, very high, you can see that the losses are very, very high. Suppose if you pass a 1 megahertz frequency, up to 1 meter, you can ignore the cable loss. But what will happen in the same 1 meter cable, if you pass 100 terahertz, more than 100 terahertz frequency, at 1 meter only, you can signal will going to decay by 80% to 90%. So if you use a normal coaxial cable at terahertz frequency range, the losses will be very, very high. That is the reason why you cannot use. So when you see the structure of the optical fiber, it looks like this. Basically, it is a, what you can say, it's a concentric cylindrical sections, you can say. So the first layer will be the core, what you can call, and the core will be surrounded by the cladding material. And then there is a small outer layer, which will be nothing but a protection layer, you can say. So this is your cross-sectional view. Whatever I have drawn is a cross-sectional view. This is from the front side. If you look at it, so you look like that, or you are going all the circles, because the core cladding will be purely all about cylindrical sections. So when you look from the front side, you can see that the core is of a circular area surrounded by a cladding. And then this is your outer protection area, just for the safety, for the oscilloscope. The main reason how the signal propagates in optical fiber is through the property of the total internal reflection. Now, in order to have a total internal reflection, the wave should travel from rarer to denser or denser to rarer.
Denser to rarer.
Yeah, which means that, see, this is your core medium and this is your cladding medium. So the core permittivity should be higher compared to the cladding. Agree with me? So in optical fiber, the total internal reflection takes place provided your core refractive index, or you can say the core relative permittivity, is much higher than that of the cladding. So whenever it is traveling from denser to rarer, you can see when it is incidenting here. So since your denser medium to rarer medium, it will fully get reflected back. So like this, the wave is getting to be propagated in a optical fiber. So this process is called total internal reflection. Now generally when you see the core is basically made up of a glass, or you can say it's a plastic material. And even though the cladding is a mixture of a glass composition with a less refractive index. Both are actually, it's a glass material only. One will be the higher, you can say higher permittivity, and this one will be the lower permittivity. And there are different type of optical fibers, there is a step index fiber, graded index fiber, all these things would have been studied already. So first of all, what do you mean by step index fiber? Is nothing but the refractive index is going to be uniform throughout the medium. So suppose when you take about cladding material, you know that if the refractive index is uniform everywhere, irrespective of the position, then you can say that those fibers are called step index fiber. Suppose if the refractive index varies from the axis, so let us assume that this is your axis, and in this particular direction, if your refractive index varies, which means you will have a relative permittivity 1 here, relative permittivity 2, relative permittivity 3. So if you will have a discontinuity of refractive index, those kind of fibers are said to be graded index fiber. So I will not go much deep into that. So whatever is required for the subject, I can explain. And you also know optical is a 1 semester subject. I think you would have been studied about this. So the basic difference between step index and graded index was, if the refractive index is uniform in the cladding material, that is said to be step index. And if the refractive index are basically varying, you can call it graded index. Okay. And first of all, what do you mean by refractive index? So the refractive index, generally, if you see here, if you take refractive index of any medium, that is defined as velocity of light in that medium divided by free space velocity. You know that the core and both are dielectric materials. So what is the velocity in a dielectric material? Can you tell me what is the velocity in a dielectric material?
The C by epsilon root over.
Yeah. This is reverse actually. Velocity of light in air divided by velocity of light in medium. Sorry. Written it wrongly. Okay. So velocity of light in air is nothing but free space C, and velocity of light in the glass is C by root epsilon r. So the refractive index is nothing but root over dielectric constant. Okay. So the refractive index, when I say, it is nothing but square root of the dielectric constant. So it is basically defined as the ratio of velocity of light divided by the velocity of that wave in that medium. So if it is dielectric, you can take it as C over root epsilon r. So when I say higher permittivity, which means it's a higher refractive index. And here you should not get confused with the symbol called what we have done, eta. So it is not eta. I have represented the symbol called n. So the refractive index basically defines a measure of the permittivity in that medium. So I can say that core is having more refractive index, which is more permittivity, and the cladding is having a less refractive index, which is less permittivity. And we have seen the total internal reflection takes place provided whatever the angle of incidence at this particular junction, I can call, this should be greater than your critical angle. Agree? Because the angle of incidence at this point, if it is exceeds the critical angle, then only the wave can get reflected back. Suppose if the angle of incidence is lesser than critical angle, the wave will not reflect it back and it will propagate into the next medium. So you should remember the point here If the angle of incidence at this point is more than the critical angle, then you can expect that the total internal reflection gets occurred. Okay, now this is very, very important. You have to concentrate here. First of all, you can see here, once the wave is entered inside, you cannot control. Whatever the angle it has to be here, see, whatever the angle it has to be here, it has to be controlled basically through the angle of incidence at the optical fiber. So let us assume that the wave is entering from the free space onto the optical fiber. What should be the minimum angle of this one in order to have the critical angle to exist? Can you tell me what should be the minimum value of this one to have the reflection? What should be the minimum angle of incidence here?
Root epsilon.
Root epsilon. How?
So 1 by root epsilon or 1 root epsilon?
No. What I was asking, what should be the angle of incidence here in order to have a reflection?
Theta C.
Correct, right? So your angle of incidence has to be equal to critical angle. First of all, what is the critical angle equation here between these? So you can say, instead of N1 and N2, let me write it as refractive index of core and refractive index of cladding. Okay. You know, between two different mediums, we already know the Snell's law, sine theta I divided by sine theta t is equal to root over epsilon r2 divided by epsilon r1. So the minimum angle here, it should be equal to critical angle. So what will happen right now? And theta t should be 90 degrees when you are defining the critical angle. So sine theta c is equal to refractive index of cladding divided by refractive index of core. So any questions here, this point? Is it clear? So what I was defining, in order to have a total internal reflection here, the minimum angle of incidence at this point is nothing but critical angle. So what should be the critical angle exist here is nothing but sine theta c should be the ratio of the cladding refractive index by the core refractive index. Now, you can see here, this is your theta c and this is your 90. And what about this angle right now? I can say here that this is equal to 90 minus theta c. Okay. Now, I was calling this particular angle as a theta a, which I can call it as an acceptance. So, what is the Snell's law between your air and core? So, when I was applying the Snell's law between my space and core interface, using our second Snell's law, what it says, sine theta I divided by sine theta t is equal to root epsilon r2 divided by epsilon r1. So this I can call it as n2 divided by n1 only. So in other words, n1 sine theta I is equal to n2 sine theta t. This is very important. You have to focus here. So in this case, the first medium is free space. So what is a free space refractive index? You can see here, the first medium is a free space, second medium is the core. So what is the refractive index of the core? Air. What is the refractive index of the first medium?
1.
Yeah. So in that case, what will happen if this is 1 and what is the angle of incidence here you are getting? That is nothing but your acceptance angle theta a is equal to. So n2 is nothing but your refractive index of the core. Okay. N core into sine of. What is your transmitted angle here? This is nothing but your 90 minus theta c. So this is basically called numerical aperture. So I will tell you what do you mean by numerical aperture was. Just listen here. You know that theta A and 90 minus theta C will be directly proportional. Okay. Now what will happen if suppose the angle of incidence at this particular point is greater than my angle. So since your theta A and 90 minus theta C both are proportional, because you can use your Snell's law, you can say that this angle and this angle are proportional. When theta A increases, what will happen? Your 90 minus theta C increases, which means your theta C get decreases. Are you getting my point? What I'm saying? Suppose if the angle of incidence is more than this acceptance angle, your 90 minus theta C is going to be increased, and accordingly your theta C will come. So suppose if it is coming down below the critical angle, will you have total internal reflection?
No, sir.
Now, that means what is the maximum input it can enter here? If suppose I should get the angle of incidence here, it should be less than critical angle. That should be controlled provided I should not exceed this angle. If suppose whatever the wave it is entering, if it is going to exceed the acceptance angle, it is coming down below the critical angle. So it is a problem. So if you form a cone, you can see here, if you form a cone with a maximum acceptance angle of A. So what it represents, when any frequency falls within this acceptance angle, then only the total internal reflection takes place. If any of the frequency is entering with more than the acceptance angle, here whatever the angle of incidence here you are going to get is going to be lesser than the critical angle. So then it cannot propagate. So what is this numerical aperture says was, what is the maximum acceptance angle it is allowed when the wave is traveling from free space. Suppose if it is exceeding the acceptance angle, you cannot have any total internal reflection. Is it clear?
Yeah. Also,
Yeah.
we measure all the angles with respect to the normal.
Correct.
Be it theta or theta t or anything.
Yeah. Even you can see here, this is your normal only, right? Whatever the acceptance angle I measure, normal only.
Okay. Yes.
Yeah. Even if you see here, this is also normal only.
Okay.
But when you are measuring, no, these two you are measuring. So this is your normal. Okay. Yeah. That's it. So the condition here was what numerical aperture represents. It is the maximum acceptance angle. If any frequency falls within this zone, then only it can propagate. You got my point?
Yes, sir.
Yeah. If any frequencies, suppose my acceptance angle is 50 degrees, and if the wave is trying to enter at 60 degrees, it cannot do. It cannot go because the process of internal reflection doesn't take place. So whatever, if you want to have a total internal reflection here, it should be controlled by this only. And one more thing, one small, this one I need help from you. I need another 6 minutes of time. Okay, I will be able to finish this. So just bear with me for some time. Numerical aperture is the sum of the maximum acceptance angle that will be equal to, okay, sine theta c is equal to refractive index of the core into cos of theta c. Okay. So just I will write down here, numerical aperture is equal to the sine of the maximum acceptance angle equal to the refractive index of the core into sine of, cos of theta c. You can see here sine 90 minus theta c is cos theta c. And you know that if you want to write in terms of refractive index also, you can straight away, because this can be 1 minus sine square theta c. We already defined what is the critical angle. So using that formula, 1 minus n cladding divided by n core whole square. Okay. So the numerical aperture, you are going to get it as, you can simplify that, root of refractive index of the core square minus cladding square. If you know the refractive index, you can straight away use this formula to calculate what is the numerical aperture. So this is very important, you have to understand. So the numerical aperture represents what is the maximum acceptance cone that is present in the optical fiber. If your angle of incidence is exceeding that acceptance cone, it is not propagated. Okay. And especially when it comes to multimode optical fibers. Okay. What do you mean by multimode optical fibers was, you can launch a number of frequencies at the same time into the optical fiber. Okay. But the main problem with the multimode optical fibers was the dispersion. The dispersion is nothing but, see, when you have your optical fiber, you are trying to launch a number of waves. So there is an interference from the one wave to the other wave. That is basically called the dispersion. But what is actually, how you can launch multimode optical fibers was, main thing in communication you would have been seen, optical fibers are preferred because your bandwidth is less. Within the same small bandwidth, you can launch a number of waves together. Okay, thereby you can improve the communication efficiency. So in a multimode fibers, there are two things which you have to understand. Suppose if I want to launch a more number of signals in this fiber, that is said to be multimode optical fiber. That is basically depends based on the mode volume. So what is basically mode volume? I can define it as a mode volume. First thing, you can launch more number of modes or more number of waves into the optical fiber, provided your numerical aperture is much higher. Will you agree with me? See, suppose if I had more acceptance angle here, if I had a more wider range, I can launch more number of waves. Agree?
So, but it depends on the bandwidth, right?
No, bandwidth. It's normal when you take any frequency. If you take, it is having a single bandwidth. But what I take, I will consider the same frequency and 100 number of signals. Let me say I was passing a 1 terahertz signal and 100 number of frequencies are there. 100 signals are there corresponding to same frequency.
Yes, sir.
In that case, what will happen? I can say that I can launch more number of waves provided if my acceptance angle is high.
Yes, sir.
So which means your numerical aperture of the fiber is very high.
Yes, sir.
And at the same time, it basically inversely proportional to the wavelength. Correct? Huh? Suppose if you take a low frequency, your wavelength will be very large. See here, what I was trying to say, it is inversely proportional to the wavelength. Why it is? Suppose if you launch a high frequency signal, your wavelength will be very less.
Oh, okay, sir. Yes, sir.
Since your wavelength is very less, you can say more number of waves. Because if the wavelength is very large, it cannot fit into the fiber.
Okay.
Yeah. So that's the reason why if the wavelength is less, you can launch more number of waves. Correct. And at the same time, one more thing is, if the diameter of the core, you can see here, whatever the core, if the diameter is large, then also you can pass more number of waves, right? If the width of the core is slightly high, you can launch more number of the waves. So what I can say? It is proportional to the core diameter. It is proportional to the numerical aperture, inversely proportional to the wavelength. So based on that, I will straight away give the formula. So if you see that, pi d by lambda into numerical aperture. So that is what you will see a basic derivation in optical fibers. But just with the help of some explanation, I was straight away writing that. Okay, so the mode volume is basically defines how many number of modes can be transmitted into that way. So the number of modes supported by the fiber is equal to mode volume square divided by 2. Actually, there is a derivation is there, but I don't want to discuss about that. So how many number of modes are supported in the fiber is basically depends on the mode volume. And the mode volume is directly proportional to diameter of the core, numerical aperture, and inversely proportional to the wavelength. Okay. So let me discuss one problem, then you can understand it better, I hope. Last one. See the case. There is a step index fiber has a core diameter of 80 microns and a core refractive index of 1.62 and numerical aperture 0.21. So then calculate what is the acceptance angle. And the second thing, refractive index of cladding and how many number of modes are supported in that fiber. The first thing is what? Core diameter has been given 80 micrometer and refractive index of the core has given 1.62 and the numerical aperture is equal to 0.21. So then calculate what is the acceptance angle. So we know that the numerical aperture is simply the sine of the acceptance angle, sine theta A. So from this, your acceptance angle is equal to sine inverse 0.21. Tell me what is the value you got? Quickly do and tell me what is the value. So shall I write here? Will you verify later? Yeah, you can get 12 degrees approximately. Okay. So the next thing, what is the refractive index of the cladding? We know the numerical aperture in terms of the refractive index, right? Root over refractive index of the core square minus refractive index of the cladding square. So numerical aperture is equal to root over n1 square minus n2 square. So you can straight away calculate what is the cladding value. So how much you are getting here? Let's quickly do that. What is the value you are going to get? So the refractive index of the cladding, if you are calculating it, you can say root of 1.62 whole square minus 0.21 square. Anything you got? You can verify anyhow. You are going to get 1.606. So, but here you have to observe one thing. See, as I mentioned, the refractive index of the core is higher than the cladding. But see, you can see here, there is not a drastical change. It is slightly higher because you know the core and cladding, both the materials are made up of same composition. It is also made up of glass and cladding also made up of glass. So that is the reason why there, of course, core refractive index is high, but not that much. So almost it's comparable. Okay. And the next thing, third one, you can see how many number of modes are supported by the fiber if the wavelength is 0.8 microns. So in order to do that, first to calculate the mode volume, that equal to pi d by lambda into numerical aperture. So all the values are given. So pi into d is 80 microns and lambda is 0.8 microns into numerical aperture is 0.21. Tell me what is the mode volume you got? $65.9. Good. 65.9. And by using that, what is the number of the modes you can say? The mode volume square divided by 2. So the mode volume you already got. So the number of modes will be n is equal to v square by 2. So what is the, how many number of modes you are getting? Approximately you can say 2170 something. Okay, these many number of modes you are getting. Okay, so actually this thing is when you are talking about the optical fiber propagation, till now there are no questions in this optical fibers. But the thing is, why I have discussed, at least you should know some of the basics. That is the reason why I have added this part in the syllabus. And because even if you see the syllabus also, that topic has been added. Propagation of light in optical fibers. So at least you should know the basics. But the reality is you should also understand, you know, that when I talk about optical fibers and antenna theory, you can cover the whole syllabus in the entire semester. Okay, that and all not required for the gate point of view is concerned. But if suppose by keeping it in mind, if I completely ignore this, I'm not doing the justice for this. Right. So that is the reason why just at least if you go through this optical fiber, at least you can understand 3-4 parameters and nothing very complicated here. Numerical aperture, what is the critical angle, and then what is the number of modes and then mode volume. So just it will take only 10 minutes time to revise this. So at least you can confidently say that I have completely covered all the topics in the syllabus. Okay. And if there is any question asked in optical fibers also based on fundamentals, you will be able to do the answer. So that is the reason why I have started this. Actually, if you go to any other institutes, they can simply skip all these topics and that. But the thing is, whichever has not, since optical fiber has not asked in the previous year, is there any guarantee that next year also they may not ask? Definitely, it cannot be there, right? So that is the reason why I was covering. My intention is to cover all the things. And one more thing, as I told you in the last class only, in the GATE 2021, there is an update of circular waveguides, right? Have you seen that syllabus? There is optical fiber circular waveguide. They can say cylindrical. It is a kind of waveguide is different and optical fiber is different in my opinion. The reason because whenever you are talking about waveguide, you are talking about the energy in the form of electromagnetic waves. Whereas when I was talking about optical fibers, it is a basically concept of photonics, where the energy you can say it is a propagation of the light. So rather than the wave nature, you can say photonic nature. So there, if you want to study about the optical fibers, you know, it's all about quantum physics. So where you are talking about quantum theory and then photonics theory, all these things and all. So both are different, actually, in my opinion. But if we see the physical arrangement and all, it is more or less same. But the complete discussion, what we are discussing in circular waveguides is different. So what point I would like to give you was the circular waveguides. My plan is just I will create one presentation. Okay. And in the next class, I was going to discuss about antennas and I will complete the part. And after that, you will have 20 to 25 days for the revision part. Of course, other simultaneous classes also will be going on. And you are supposed to practice whatever the concepts I discussed in the electromagnetic theory. And after that, there will be 2 more classes will be there and purely dedicated for the problem solving. So what I told to Dinesh sir was, I will give a sufficient time for you people so that you can say 20 to 25 days. You go through the complete whole theory, all the classroom notes, whatever I have said, and you be ready for that class. So in that class, actually my plan was I will take first 15 to 20 minutes. Okay. Then I will try to explain what is the concept of circular waveguides in a basic. Because once again, I was talking about circular waveguides is a fully mathematical Bessel's function. All these things will be there. If I tell all these things right now, you will run away. So I also need some time to make it and to put it in a very simple format. So anyhow, we will have 20 days time. So where we can discuss about the problem solving. That time I can discuss the first 15 minutes I can dedicate for that topic. Then we'll go to the revision. That is how actually the curriculum has been planned. Okay. So with this, actually, almost like your 95% of the syllabus is covered, except for the antennas. So antennas, it is only some 2 to 3 hours it will take. So that we can discuss in the Sunday's class. Okay. So I will upload this presentation now only. So you can go through the complete waveguide part and the optical fiber and make a short notes in this chapter. So in the next class, we will dedicate only for the antennas. Okay. It's already late. So we can, if you have any doubts, we can discuss, anybody. Yeah. Yes, yes.
Just a question about delta operator. Delta operator, we know that it's just the form of the rate of change. Right? In that case, that suppose in rectangular system we write about del x, dou x, x, dou x, dou y, ay.
Okay.
That comes to, my question is that itself it is vector or cannot say
it's a vector. It's basically del is a vector operator. Ideally speaking.
Operator.
Correct.
So in this case, suppose this rectangular del x of ax will be 0 if I consider that only this vector only, right? Because ax direction there will never will be change, right? Always constant.
No. Suppose for that particular vector, if the coefficient is a constant.
Yes, one.
Constant means there is no rate of change. You can straight away take 0.
Yes.
Correct.
Yeah, that's why that I'm asking that am I telling correct that only when it is 1 then only it is 0. Otherwise that whatever will be the function depending on that it will give some value.
Exactly. If it is a constant, it will be 0.
Yes. But sir, in that suppose circular coordinate or cylindrical coordinate, in some cases it will not be 0, right? Because there will be some suppose
scaling
A5.
factors. Correct. There will be a scaling factors.
Sir, concept you told me that del, suppose we take del cross some vector. So in that case, del is, the rate of change of del is in the direction of phi, right?
In which
You
case?
said, suppose magnetic field, if I take means del cross H equals to J. In that case, del rate of change is in the direction of phi because H also has the direction of phi, right?
No. See, what is this actual equation? No. Whatever I have told in that magnetostatics, if you remember, I told like this. The direction of magnetic field will be the cross product of current into radial direction. This I have told, right? If I am not wrong.
Yes.
So suppose if the current is flowing in the z direction, what will be the magnetic field direction here? Current is in z. Radial direction means when you move perpendicular to the source.
Yes.
So in this case, AZ cross arrow, if you take, that will be in phi direction.
Yes, sir. That my question is about the del operator. Del operator is used here also, right? In this magnetostatics.
This case, I will agree. What will be the magnetic field direction in this case, and what should be your
Magnetic
current direction?
is phi direction, and suppose z direction is current direction. Okay. In that case, what is the direction of the del operator? Is it the phi direction, same direction?
No, magnetic field is there in y direction. Can you repeat it again? And z direction will be
in phi direction, and J is z direction.
Okay. Yeah.
So in
then
that
in this case, your del will be in the direction of rho.
Okay.
Because if you take
in
phi
radial
again,
direction.
Yeah, in the radial direction. Yes, that's what I was saying. Because suppose if you take phi, your current density should reflect 0. Because you are telling that current direction in z direction, so your del should be accordingly in the direction of rho, radial direction.
Understood.
Yeah.
Yeah, just I had confusion in this. Okay,
Yeah, sure. Right. Okay. Other than that, one thing, it's already late. If you had any doubt, we can discuss in the group, or otherwise, anyhow, we are going to continue, So maybe in the next class, I will be able to clarify some of your questions. And after that, 2 more lectures we can completely dedicate for the problems. And one more small announcement I would like to make. See, once the class is over by the next Sunday, after that you are going to have 20 days. Okay, within 20 after 20 days time, the problem practice session or revision class will be there at any time. It will be a surprise. So that regarding the class communication may not be informed to you. Okay, just it will be like a surprise. So why I have planned like that was just I want to test what is your preparation level. So that is the reason why I already told to Dinesh sir that he will not be able to communicate when that preparation class is going to be there. Just one day before you will be able to be communicated. Okay, then you can practice. And I want to understand actually what is your understanding about EMT and all. So that is the reason why it is going to be a surprise class. Okay, then it's already late. You can sign out right now. See you in the next class. Good night.